Design on RCC column footing with the following data. Column 400 mm by 400 mm. Shape bearing capacity of soil 200 kilonewton per meter square. Load on column it is 1200 kilonewton. Concrete M20 and Fe415 steel is used. Calculate depth of footing from the BM criteria. Okay. So first of all, write down the given data. Size of column it is given. Size of column it is 400 by 400 mm. 400 mm by 400 mm. 400 mm by 400 mm, that is 0.4 meter. 0.4 meter. Okay. Then SBC of soil it is equal to 200 kilonewton per meter square. 200 kilonewton per meter square. Then load on column, that is load on column it is given P is equal to 1200 kilonewton. Okay. And factored load of column PU is equal to P into 1.5. So P it is 1200 into 1.5. It will be 800 kilonewton. It will be 1200 into 1.5. It will be 800 kilonewton. Correct. It will be 800 kilonewton. Okay. So next it will be SPC of soil 1200 and M20 grade of concrete given. That is FCK is equal to 20 Newton per mm square. 20 Newton per mm square. 20 Newton per mm square. And grade of steel it is given Fy is equal to 415 Newton per mm square. 415 Newton per mm square. And calculate depth of footing from BM type. So this data it is given for design of RC column footing. Okay. So we'll solve by step. Okay. So step one, ultimate bearing capacity. Step 1, ultimate bearing capacity. Ultimate bearing capacity that is in bracket UBC. Okay. UBC is equal to 2 into SBC. So 2 into 200. UBC is equal to 200 it will be 400 kilonewton per meter square. 400 kilonewton per meter square. Okay. So this one it is UBC of footing. Then step number 2. Total load on footing. Total load on footing. Total load on footing. That is in bracket WU. Okay. So self weight of footing, assume 5% of column on load. 5% of column on load as self weight of footing. Self weight of footing. Okay. We just assume the 5% of column load as a self weight of footing. So WU is equal to so 5% means 1.05 into the factored load on column it is 1800 kilonewton. 1.05 into 1800, it will be 1890 kilonewton. This one it is total load on footing. Okay. And step number 3, area of footing. Area of footing. That is we can say it is AF. area of footing. So AF is equal to total load on footing, total load on footing, total load on footing divided by total load on footing divided by UBC of footing, ultimate bearing capacity of ultimate bearing capacity, ultimate bearing capacity, ultimate bearing capacity. Then total load on footing it is 1890, that is W. You can say it will be written down here W divided by ultimate bearing capacity, that is UBC, Okay. So AFW it is 1890 kilonewton divided by UBC it is 400 kilonewton. 400 kilonewton per meter square. 400 kilonewton per meter. You get the area of footing. Area of footing 1890 divided by 400 will be 4.725 meter. 4.725 meter square. 4.275 meter square. This one it is area of footing. And step number 4, size of footing. Step 4, size of footing. Step 4, size of footing. Size of footing. That will say it is B. Capital B. Size of footing will be capital B. Capital B is equal to size of footing, it will be actually this footing it is square footing. Means root of AF. Root of AF. Root of AF. Root of AF. That is equal to root of AF means is equal to root of AF it is 4.725. 4.725 meters square. So B is equal to 4.725 root of 4.725 to be 2.17. 2.17. So round the figure it will be take 2.2 meter. 2.2 meter. So provide size of footing. Provide size of footing. Size of footing 2.2 meter by 2.2 meter. 2.2 meter by 2.2 meter. 2.2 meter. So this one it is size of footing. Okay. Step number 4, upward soil pressure. Step number 5. Step number 5, upward soil pressure. Upward soil pressure. Upward soil pressure. That is in bracket small p. That is in bracket small p. Small p. Small p is equal to total load of factored load of column. Factored load of column. Factored load of column divided by factored load of column divided by size of footing. Size of footing, that is provided size of footing. Size of footing. Size of footing. Okay. So factored load of column it is PU it is 1800 kilonewton divided by size of footing it is 2.2 meter by 2.2 meter. 2.2 meter by 2.2 meter. Okay. So P is equal to 1800 divided by 2.2 into 2.2. It will be 37.371.900 kilonewton per meter square. So this value should be less than the ultimate bearing capacity of column, that is ultimate bearing capacity of soil, that is 400 kilonewton per meter square. Then it is okay and safe. Then it will be okay and safe. Otherwise, we require the revised size of footing. Okay, so this then it will be okay and safe. Okay and safe. Okay. So step number 5 we have completed. Step number 6, bending moment. Step number 6, bending moment. Step number 6, it is bending moment. Okay. So bending moment, we need to calculate bending moment. Okay. So actually, so putting it is just like it is acted as a cantilever action. That is putting it. Okay. The actual this one cantilever action it will be act. Okay. Cantilever action. So this one and it is fixed. So total width of footing it is 2.2 meter. Total width of footing it is 2.2 meter. Capital D. Okay. So here it is 2.2 meter. 2.2 meter. Column size it is point. So what is column size it is 0.4 meter. 0.4 meter. Okay. So we need to calculate this distance. This distance just assume it will be x. This distance we just assume x distance. Okay. From this side it is x. So from this side it is also x. This one it is also x. This one side it is also x. This side it is also x. This side it is also x. So we need to find out the x distance. X is equal to capital B, that is width of footing, minus small d, width of column, that is 0.4, divided by 2. Why it is 2? Because it is both sides. So x side it is both sides. X distance. Okay. So capital B minus small b divided by 2. It will get x side and this x side. Okay. So x is equal to capital B it is 2.2 meter. 2.2 meter minus small b it is 0.4. 0.4 divided by 2. 0.4 divided by 2. Divided by 2. It will be get x is equal to 2.2 minus 4 divided by 2. So it will be 0.9 meter. 0.9 meter. Okay. So now because of cantilever action, the bending moment Bm is equal to px square by 2. Px square divided by 2. P into x square. Px square divided by 2. Px square divided by 2. Px square divided by 2. Divided by 2. So P it will be upward pressure it is 371.900 into x it is 0.9 square 0.9 square divided by 2 divided by 2. So Bm is equal to 371.900 into 0.9 square divided by 2. It will be 150.619 619 kilonewton meter. This one it is bending moment. Just I will note down this Bm is equal to 159.619 kilonewton meter. Okay. So now calculate depth of footing based on Bm criteria. So step number 1, how much Bm? Step number 7. Step number 7. Step number 7. Depth of footing based on Bm criteria. Step number 7. Step number 7. Depth of footing. Depth of footing. Depth of footing based on Bm criteria. Based on Bm criteria. Based on Bm criteria. Criteria. Okay. That is depth of footing. It is effective depth. That will be small d. Small d. That is effective depth. Okay. So for that, equate Bm is equal to equate Bm equal to mu limiting. Okay. So Bm is equal to mu limiting for Fe415 it is 0.138 into FCK into B into D square. 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 So Bm it is 150.619. 150.619 kilonewton meter converted is in Newton mm. So 0.138 into FCK it is FCK it will be 20 into B it is 1000 into D it is we need to calculate D value. Okay. D square. Okay. Small d is equal to 150.619 into 10 raised to 6 divided by 0.138. FCK is 20, B is 1000. So D is root answer will be 233 mm. 233 mm. Okay. 233 mm. Find out overall depth of footing. Step number 7. Sorry, step number 8. Overall depth of footing. 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 That will be capital D. Capital D. Capital D is equal to small d plus cover plus 5 by 2 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 plus 5 by 2. So is equal to, just assume cover 50 mm. Assume cover 50 mm. Okay. Capital D is equal to, assume cover 50 mm and diameter of bar 16 mm and diameter of bar 16 mm. 16 mm. Okay. Capital D is equal to small d, it will be 233 mm. Cover it is 50 mm. Diameter of bar 5 by 16 it is 8 mm. Okay. Capital D is equal to 233 plus 50 plus 8. It will be 291 mm. 291 mm. Round the figure, it will be take 300 mm. 300 mm. Okay. 300 mm. Round the figure, take 300 mm. So small d is equal to effective depth. Capital capital D minus cover minus pi by 2, 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 minus pi by 2. Capital D it is 300 mm, minus cover it is 50 mm, then minus pi by 2 it is 8 mm, but it is 8 mm. 300 minus 50 minus 8, 242 mm. Small d it is 242 mm. Actual effective depth. Okay, actual effective depth. I will note down this value also. Small d is equal to 242 mm. 242 mm. Then step number 8. Area of the main reinforcement in both direction. Step number 8. Sorry, step number 9. Main reinforcement in both direction. Step number 9. Main reinforcement in both direction. Main reinforcement in both direction. Main reinforcement in both direction. Both direction. Main reinforcement in both direction. Okay. So AST is equal to, so standard formula just write down. AST is equal to 0.5 into FCK, 0.5 into FCK divided by Fy, divided by Fy, divided by Fy in bracket 1 minus root of 1 minus 4.6 into 4.6 into mu divided by FCK BD square divided by FCK into B into D square, B into D square, bracket close, B into D, bracket close, B into D, B into D. Put all this value here. 0.5, FCK will be 20, Fy will be 415, Fy will be 415 in bracket 1 minus root of 1 minus 4.6 into mu, it is mu 150.619 150.619 into 10 to the power 6, 10 to the power 6 divided by FCK, it will be 20 and B it is 1000 into B it is 242 square, 242 square, 242 square, 42 square. Then B it is, B it will be 1000 into B it is 242 mm. Okay. You get the AST formula. So AST is equal to, so first solve this under root 4.6 into 150.619 into 10 raised to 6 divided by 20 into 1000 into 242 square, 1 minus answer, then root 1 minus answer, then is equal to 0.5, FCK will be 20, divided by 415 into 1000 into 242. That will be AST 2104.196 mm square. This one it is area of tree. So I will note down this value. AST is equal to 2104.196 mm square. Okay. Then spacing. The next step, spacing. Spacing from spacing of main reinforcement. Then step number 10. Step number 10. Spacing of main reinforcement. Spacing of main reinforcement. Spacing of main reinforcement. Spacing of main reinforcement. Okay. So spacing is equal to so just first of all assume 20 mm diameter of bar. Assume 20 mm diameter of bar. Assume 20 mm diameter of bar. So Fi is equal to area of one bar is equal to pi by 4 into 20 square. 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 So if pi by 4 into 20 square, it will be 314.159 mm square. Spacing is equal to we note that formula 1000 into Fi by 8. 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 Fi by 8. So 1000 into Fi it is 314.159 divided by AST it is AST area of steel in tension. We are calculated it is 2104.196. Calculate spacing. Spacing is equal to spacing is equal to 1000 into 314.159 divided by 2104.196. It will be 149.301. Provide 20 mm diameter of bar. 20 mm diameter of bar of spacing 140 mm center to center 140 mm center to center 140 mm center to center in both direction 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 in both direction. This one it is design of footing. Design of RCC column footing when axial loaded column. Okay. So provide 20 mm diameter of bar of spacing 140 mm center to center in both direction.